nuclear reactions. Certain species after suitable bombardment undergoes a change in the character. That means the character of the species will change when they are suitably bombarded with some particles. That particle, the striking particle may be proton, neutron, alpha particle, electron, or any nucleus. So these are called striking particles, also called projectiles. So we can call it as projectiles because we are projecting this on some nuclei. Here, in general, this nuclear reaction is denoted with this equation. When A, this is the striking particle or projectile, bombarded with the nucleus of an atom X, it converts into Y here. That means its character will change and it emits one more particle here, either by giving energy or by absorbing energy. So this is a nuclear reaction equation. For example, if you take a alpha particle when bombarded with nitrogen, this is stable. When it is bombarded with this one, it will produce one unstable nuclei. This is stable nucleus. So it once again converts into 8O17, which is stable here, and it produces a proton. Here this is the proton. So here both A as well as B are protons or neutrons or alpha particle or electron or any one nucleus. So these two are belongs to this category. Now there are 4 types of nuclear reactions. The first one is photonuclear reaction. We know what is this photo. Photo is nothing but light. Reactions in which the photons causes the target nucleus to change its form or to change its character. For example, if you send a gamma photon onto this 1H3 tritium, it produces 1H2 deuterium, and it also produces one neutron here and exerts some energy. Here, as I said earlier, these may be one proton, neutron, alpha, this, or even a gamma photon also. So this is called a photonuclear reaction. So this takes place with the help of photons, and this character will change from 1H3 to 1H2. Similarly, the second one is a scattering reaction. So what is this scattering reaction? In this scattering reaction, the target nucleus as well as the product nucleus remains the same. So there is no change in the character here between the target and product. Character will not change, but energies will be exchanged between them. Here, this is a projectile projected onto 3 lithium-7, produce 3 Li7 only, but it produces a proton, and it is producing some energy here in the form of light. So this gamma photon is nothing but light energy. So this is called scattering reaction. Here you can see this is the target nucleus and this is the product nucleus. Both are same, but their energies will be exchanged here. Now, third one, nuclear fission reaction. The fourth one, nuclear fusion reaction. So in this lesson, we are going to give more concentration about these two reactions. So this, for the namesake only, we are studying these two. So what is this nuclear fission? Fission is a splitting of a heavy nucleus. This is a splitting of a heavy nucleus into 2 or more nuclei of almost equal mass with the release of energy. So for this, let me use this equation here. For example, 92 uranium-235, which is stable here. This is a stable nucleus of uranium. When bombarded with any one projectile, here the projectile is a neutron, so 0N1, then it produces 92 uranium-236. Remember, this is a stable nucleus. When bombarded with a neutron, it produces an unstable nucleus. This 92 uranium 235 is unstable, and after splitting, it converts into 56 barium 141, 36 krypton 92 plus, 3 more neutrons plus 200 million electron of energy. So this is the equation for the nuclear fission. Here, whenever this stable nucleus bombarded with a neutron, it is producing two product nuclei as well as some particles that are emitted in this reaction, just like here neutron is emitted, here proton is emitted, here 3 neutrons will be emitted on average, plus it is producing this much of energy, which is equal to 200 MeV. Similarly, what is this nuclear fusion reaction? Here heavy nucleus present to 2 or more, here 2 or more smaller nuclei combine to form a heavy nucleus. So in this we can write 4 protons when combined together will produce 2 He4 plus. It produces 2 positrons also plus 2 gamma particles, nearly 28.4 mega or million electron volts. This is about fusion. So now I am going to explain about this fission as a fusion in detail. In nuclear fission, according to the equation 92 uranium 235, when bombarded with a neutron, this we call it as slow neutron. Here this will produce 92 uranium 236. But once again, as I said earlier, this is unstable, which is split into 2 more stable. This is also stable nucleus. So here this will be 56 barium 141, 36 krypton 92, and 3 more nuclei plus 200 million electron volts of energy. Now these are also called thermal neutrons here, also called fast moving neutrons. Now every time when these two combine, or when this is bombarded with neutron, we may not get the same set of final products here. These products may change. Here, for example, if you take 92 uranium 235, when bombarded with 0N1, generally it gives 92 uranium 236, which is equal to unstable here. So this is the stable nucleus. Use 54 xenon 140. This is 38 strontium 94 plus 2 neutrons here plus some energy Q. So the final products may change, but the number of neutrons produced also may change. So after observing different nuclear fission reactions, it is found that at an average 2.5 neutrons are produced in this nuclear fission reaction. Now if you take the mass of this target nucleus and this projectile and mass of the final products here, either this or this here, it is found that mass of the reactants, that is uranium and neutron, is greater than mass of the products formed here. As there is some mass defect, this mass defect can be seen as energy released here. So this energy released is given as Q. So here Q is given by mass of reactants minus mass of products in atomic mass units into 931.5 million electron volts. So by using this expression you can find out that Q value in any nuclear fission reactions. For example, if you take the actual masses of this and this and the masses of this and this and this, then we can find this one by using this relation here. If you consider the mass of uranium nucleus, mass of the neutron, these are the reactants. So the mass of the reactants is given by 8, this is 9, 13, 4, 5, 0, 236.054398 AMU, atomic mass units. Similarly, the mass of the products, that is mass of this Ba141 is 140.9177, krypton is 91.88, and 3 more neutrons are produced here. The sum of the products, mass of the products is given by here 9, 5, 9, 10, 30, 20 here, 5, 5, 10, 17, 18, 19 here, 8, 9, 10, 11, 12 here, 9, 9, 18 here, 3, 4, 5, 9, 10, 13, this is 235.82. So it is found that the mass of the reactants is 236 point something, mass of the products is 235 point something. That means there is a mass defect here. So the mass defect in this case is given by mass defect is equal to this first masses of all these products is 236.054398 AMU minus the mass of the reactants is 235.829095. Now this mass defect is given by, the mass defect here is given by 3035, 4 minus 2 is 2, 10 minus 2 is 20. So this is the mass defect in this nuclear fission reaction. So as we are finding this energy released, the energy released is given by 0.22530 into this 931.5. So this energy, either E or Q, whatever you can write, this is equal to, this is nearly 1900. So this is nearly 200 MeVs, million electron volts here. Nuclear fission, just now we studied that mass defect is 0.22 AMU nearly, and the energy released is around 200 MeV. This energy released can be seen as the kinetic energy of the fragments elements, that is barium and krypton as well as the neutrons. After that, this energy will be transferred to the surroundings and it appears as a heat energy. So this appears as heat energy later. Now, in this case, if you observe this reaction, so this is a 92 uranium 235 when bombarded with one neutron here. So this is a neutron here. When this neutron is bombarded with this uranium here, so one neutron is bombarding with uranium, it splits into barium and this will produce one barium here and krypton here, and it produces at an average 3 more neutrons. So this is the first one, this is the second one, this is the third one. So for this reaction to sustain, each and every neutron that is produced in this reaction should collide or should hit one more uranium 235 nucleus, and this also should collide with one more 92 uranium 235. This is also one more 92 uranium 235. So this is how this reaction continues here. In each and every reaction, once again, it will produce 3 more neutrons here. I am not showing this barium and krypton here. So this will also produce 3 more neutrons here. This will also produce 3 more neutrons here. So this reaction continues like this. That means in the first generation we will have 3 neutrons. In the next generation we have 9 neutrons. In the next generation we have 27 neutrons. In the next generation we have 81 neutrons and so on. Then it will be 243 neutrons and so on. So this is called a chain reaction. A reaction in which the number of neutrons increases in a geometric progression or GP, and the number of reactions are increasing here. As a result, the amount of energy also increases. In the first case, it is producing, in this reaction it is producing 200 million electron volts. In the second generation, 200 plus 200 plus 200, it produces 600 million electron volts. In the next generation, 600 into 3, 1800 million electron volts and so on. So energy increases in GP also here, into 3. So not only the number of neutrons, the energy is also increased by 3 times in each generation. So here we have neutron multiplication factor. Neutron multiplication factor. This we denote with the letter K, which is given by number of neutrons generated in present generation, number of neutrons produced in present generation by number of neutrons produced in previous generation. So now let me take this one. In this generation, number of neutrons produced are total 9, and in the previous generation, number of neutrons produced are 3. So for this reaction, this K can be written as 9 by 3, which is equal to 3. If K is greater than 1, if neutron factor is 1, then chain reaction continues and the amount of heat produced or energy produced will be too heavy, too high. So this is a chain reaction takes place and chain reaction continues here. Suppose if K is equal to 1, that means if 3 neutrons are produced here, in the next generation also, let us say if you absorb these 3 neutrons by some methods, if you absorb these 3 neutrons as well as these 3 neutrons, once again it will produce only 3 neutrons here. So this absorption can be done by using cadmium rods or boron rods. These rods have the capacity of absorbing these neutrons. So even this can be absorbed. In the next generation, only 3 neutrons will bombard with this one, as well as this one, as well as this one. Once again it will produce 3 more neutrons here in this one. Here it will produce 3 more neutrons. But in each and every generation we will absorb these 3 neutrons, and we will absorb these 3 neutrons also by using cadmium rods. So by absorbing this, only 3 neutrons will continue or hit the next uranium nuclei here. So here one reaction will take place. In that, once again only one reaction will take place because these will be absorbed by some other media, and now once again one reaction will take place. So this will continue like this. So this is then K will be 1 only, because in each generation 3 neutrons are produced here, here also 3 are produced here, here also 3 are produced here, next also 3 will be produced. So this 3 by 3, K is equal to 3 by 3, which is equal to 1. This is called a controlled chain reaction. Chain reaction will take place continuously, but in a controlled manner. So controlled chain reaction takes place, and this controlled chain reaction can be used in producing electric current, electric energy in nuclear reactor. So the working principle of nuclear reactor is controlled chain reaction, and this uncontrolled chain reaction where K is greater than 1, uncontrolled chain reaction is the principle of atom bomb that we used, we have seen in Hiroshima and Nagasaki in Second World War. Suppose if K less than 1, if neutron population less than 1, then the number of neutrons produced in the next reaction gradually decreases and reaction will ceases out somewhere. Nuclear reactor. So this is the nuclear reactor. Here the main construction of this one is such that it consists of nuclear fuel. Here you can see these fuel elements which are given in black color here between the moderators. So these are the nuclear fuel. Any fissionable material can be used as a nuclear fuel. Generally we will use 92 uranium 235 or 90 thorium 230 are used as a nuclear fuel in nuclear reactor. So beside this one, actually they are sealed in aluminum cylinders. So these are kept in aluminum cylinders, and these aluminum cylinders are kept in drills bored in carbon blocks. So inside carbon blocks. So in the carbon blocks they will make some holes, in that they will keep the aluminum cylinders. Inside this they will keep this fissionable material like 90 uranium 235 or 90 thorium 230. So after that we will provide the moderator. We know that in any nuclear fission reaction, 92 uranium 235 when bombarded with the neutron, it produces 56 barium 141 plus 36 krypton 92 plus. It produces an average of 2.5 neutrons plus some energy. These neutrons are called fast moving neutrons as they have a lot of kinetic energy, and this kinetic energy is around 2 million electron volts energy. But these fast moving neutrons cannot initiate further chemical nuclear reactions. So if this kinetic energy is reduced to 0.025 million electron volts, only these neutrons which are known as slow moving neutrons, because the kinetic energy has reduced, means velocity has reduced here. So these are called slow neutrons. So moderators slow down the neutrons. So this is used to slow down the fast moving neutron. Graphite or water or heavy water is used as moderators in a nuclear reactor. So after this, here we have control rods. These control rods can be inserted in or out by using this. These are the control rods that are shown here. These can be kept inside or they can be kept out also. So these are used to absorb neutrons so that only controlled chain reaction takes place. So these are used to keep K nearly 1, that is neutron multiplication factor or reproductive factor of chain reaction. This is nearly, it is kept 1, then only controlled chain reaction takes place and a constant amount of energy can be produced in this reaction. So for this purpose we are using these control rods which are made of boron or cadmium. So after that, this coolant, here lot of heat energy will be produced for each second, and because for each second nearly 10 power 6 to 10 power 9 reactions will take, fission reaction will take place. So this heat energy can be absorbed by the coolant. Here generally we will use water or liquid nitrogen can be used as coolant, which is sent in here, and it absorbs this heat energy and will be sent out, and it use it to produce steam or to run the turbines there. And finally we have protective shield that is drawn in red color here. So this is a wall made of concrete wall made of lead blocks. So concrete plus lead blocks are used. This is a 10 meter thick concrete wall. So this is used as a protective shield. So whatever the radiations that are produced here will not be sent into the atmosphere or cannot be absorbed by the atmosphere, because it is all these radiations are absorbed by this protective shield only. So this is how we can achieve this controlled chain reaction to produce this thermal energy, converted thermal energy into some form of energy. So controlled chain reaction takes place to convert this nuclear or atomic energy, or nuclear energy here actually, nuclear energy into some other form of energy like heat energy, electrical energy, like this. Nuclear reactors can be divided into two types here. One is breeder reactor, second one is a power reactor. In breeder reactors, the reactor in which it produces or it converts non-fissionable material into fissionable material. So the breeder reactor converts non-fissionable material into fissionable material. For example, if you take 92 uranium 235 is fissionable, whereas 92 uranium 238, this is a naturally occurring or available uranium. So uranium is available in this form only in the nature, that is 98 uranium 235. Now, if you bombard this one with one neutron, it converts into 92 uranium 239 here. So this is the first reaction. In this, it produces a gamma photon also. Now, this 92 uranium 239 converts into 93 thorium 239 plus minus 1e plus 1 neutrino. And once again, this thorium, which is unstable, it emits one more electron here and converts into 92 plutonium 239 plus neutrino. Here, the material that is used in this reactor, breeder reactor, is 92 uranium 238, which is a non-fissionable uranium that is available in the nature. Finally, it converts into 92 plutonium 239, which is a fissionable material. So this material, which is 94 plutonium 239, is almost similar to this 92 uranium 235. So the final properties of this one as well as this one are almost similar here. Now, what is this power reactor? As we discussed earlier, the heat energy that is produced in a reactor is utilized by the water that is circulating here. By absorbing the heat, this water converts into steam. So this steam is utilized to run the turbines, and this in turn, these turbines will produce electric power. So the reactors that are used to produce electric power are known as power reactors. Here, the electric power produced is equal to N by 2 into energy produced in each fission. If you know the energy produced in each fission, just multiply with the number of fissions takes place per second, and this will give the electric power produced in an electric power reactors. So this is the expression that can be used to find out the electric power produced in a power reactor. Calculate the energy released by fission from 2 grams of uranium 235. Here this is the mass number. So in the solution, 235 grams of uranium contains 6 into 10 power 23 atoms. Now, as we need 2 grams of uranium, so first of all, 1 gram of uranium contains 6 into 10 power 23 by 235 atoms. Now, as we need 2 grams, just multiply with the 2 here, and this is also 2 here. So this many atoms are available here. But each uranium atom produces this much energy. So what is the energy released by this 2 grams of this one? So energy released by 2 2 grams of uranium is equal, these are the number of uranium atoms available here or number of uranium nuclei that are available here. So 2 into 6 will be, this will be 12 directly. So this 12 into 10 power 23 by 235 nuclei, and each nuclei will produce this much energy. This is 200 into million electron volts energy. So this is the energy produced in joules. But they are asking us to find out the energy in kilowatt hours. So kilowatt hours is given by kilo means 10 power 3, watt is 1 joule by 1 second, and hour is 3600 seconds, which is equal to 36 into 10 power 5 joules here. So 1 kilowatt hour. But 1 joule is equal to 1 by 36 into 10 power 5. So in place of joule I can write 1 by 36 into 10 power 5 kilowatt hours. So this energy will be 12 into 10 power 23 by 235 into 200 into 1.6 into 10 power. This power will become 10 power minus 13 by, this is the 36 into 10 power 5 kilowatt hours. So from this we can write 12 ones, 12 threes. This is 200, this 2 fours, 2 zeros, 2 fours, 20, 2. So this is 5 fours 20, 5 zeros. This is 5 fours 20, then 35, 5 sevens. So now the remaining terms are, here you can write, this is 10 power 23, 10 power minus 13, it will become 10 power minus 10. So this is 40 into 1.6 into 10 power 10 by, this is the numerator value here, and the denominator value 47 into 3 into 10 power 5. Now as this value is 10 power 5, you can write 40 into 1.6 by 47 into 3. So this is 53s are 150, 3 3s are 9. So this is 141 into 10 power 5. So the 16, 4s are 64 here. So this is 64 by 141 into 10 power 5 kilowatt hours. Of atomic energy. We have different points here. First one, the generation of electric power that already we discussed in the previous topic. That is, we can produce electric power by using nuclear fission reaction, that is a nuclear reactor. The second one is, important one is production of radioisotopes. Here, if you take that radio iron, it is used to detect and treat this anemia. And radiosodium, it is used to find the circulatory disorders in blood vessels. So if a medicine is given to a person, how this medicine is distributed throughout the body also can be detected by using this radiosodium. And also the radiophosphorus is used to treat the skin diseases, and radioiodine and iodine especially used to treat this thyroid related diseases, thyroid glands. And radiocarbon, so important one is carbon dating. Why? Because the amount of carbon that is present in a living organism and dead organisms is different. So by finding the ratio, we can estimate the age of the rock as well as earth, as well as the species that are available, and generally it is used by this archaeology department here. Now the radio cobalt, this cobalt is used to treat the cancer here. The next one, this atomic energy is also source of neutrons. So by using this, because in nuclear reactor we can produce a large number of neutrons, and by using these neutrons we can study the properties of the neutrons and the different reactions that takes place with the neutrons. And a new branch of physics in this one, which is known as neutron physics, is also developed in recently. Now the next one is to create these artificial lakes to divert the course of the river. If river is flowing in one direction, we can change the direction of this river at a particular place, to make the tunnels for laying these new railway tracks as well as roads, and also to drive these submarines as well as warplanes we are using this atomic energy, and also to produce these atom bombs and hydrogen bombs also we need this energy. Pair production or pair annihilation. First of all, what is this pair production? A photon of certain minimum energy could materialize into electron and proton. That means energy converts into matter here. So conversion of energy into mass. Here, when a photon passes through a nucleus, bombarded with any nucleus, it can produce electron as well as positron, that is antiparticle of electron here. And here, it obeys the law of conservation of energy. So energy of this one is h nu, which is equal to energy of this nucleus, because this energy will be shared by this. Some fraction of energy will be taken by this nucleus, and the energy of electron plus energy of positron here. As this energy of nucleus is nearly equal to 0, only a small fraction of energy of photon will be absorbed by this one. So h nu can be written as energy of electron, that is mc square plus kinetic energy of electron. This is the total energy of electron that is produced here, plus this is mc square, this is rest mass of the positron, this is the rest mass of electron, plus kinetic energy of positron. Now here it is found that the rest mass of electron is equal to 0.51 million electron volts. So h nu is given by m naught c square plus m naught c square, that is 2 m naught c square plus ke electron plus kinetic energy of positron. So this energy must be equal to, if you take this rest mass, this total energy will be 0.51 plus 0.51. So this is 1.01 MeV. So this is rest mass in terms of million electron volts. So h nu is equal to this plus kinetic energy of electron plus kinetic energy of positron here. If the energy of this photon is exactly equal to 1.02 million electron volts, then this pair production will take place and electron and positron will have 0 energies each. That means this energies, that is the, here it is given certain minimum energy. So what is the minimum energy required for the pair production takes place? Gamma photon must have energy greater than 1.02 million electron volts. If the energy of photon is less than this, then pair production will not take place, and this will not be produced. If the energy of the gamma photon that is striking the nucleus is greater than this, let us say this is 2 million electron volts, the minimum energy required is 1.02 electron volts. The remaining energy will be shared equally by electron and positron here. So out of this will become 0.98. So this will be 0.49 MeV. This is 0.49 MeV. So if the energy is greater than, energy of gamma photon is greater than 1.02 MeV, the remaining energy will be shared by electron and positron equally. So this is about pair production. The reverse of pair production is called pair annihilation. So here you can see a gamma photon produced electron and positron. Let us say one electron is moving in this direction, a positron is moving in this direction. If these two collide or hit with each other, then at this point we will have a gamma photon produced in this direction, another gamma photon is produced in this direction. That means if they are moving along x-axis, the photons that are produced will move along y-axis to conserve the momentum. So here what we can write, the energy of this one is m naught c square. Let us say these are at rest and collide with each other, and this is m naught c square for positron. This is equal to energy of first photon plus energy of second photon. So this is equal to 2 m naught c square is equal 2 times the energy of this one. This cancels. We know this is m naught c square, which is equal to rest mass of this one this is 0.51. So 0.51 million electron volts is the energy of the gamma photon that is produced in this one. So energy of gamma photon produced, this is equal to this much. So 0.51 million electron volts. This is called a pair annihilation. That means the mass converts into energy here.